2 is due tomorrow night. It's really short, and the homework is weighted by how long it is. You basically get a point for each correct submission. So this one's very short, and it covers what we did last week. And then homework 3, which is due Monday, a week from yesterday, is posted now, and you'll be able to do it at the end of this class, or during this class if you choose. I'm sure you can do a lot of it. And then if you missed, some of you I know are just registering, and if you missed homework 1 already, don't worry about it because you get to drop 3 homeworks. So that'll just be one of your drops. We have to do that because the answers are posted immediately. And, but I strongly recommend that even though you might have missed it, to do it again. I mean, or try it in the practice folder of Lon Kappa. So Lon Kappa has a practice folder where I put all the old homework. And so you can do it, you don't get credit for it, but you can try it and make sure you understand it because it's important for the exam to understand the material. So, and the last thing I want to say is that the bonus pre-lectures that cover basically are pre-lectures for today's lecture. I call them pre-lectures. You really should watch them ahead of time, but unfortunately I didn't post them till this morning. But generally speaking, I'll post them before the lecture. So, but they're not due till afterwards. So you can easily do these pre-lectures right after lecture. In the future, I'll post them before the lecture, so you get to do them before. So any questions before we start? Okay, so today we're doing iClickers. Now, these are just bonus points, and they're just for this lecture, the L1 section. So if you're in any other section, don't worry about them. You can get points in other ways. So we should, first of all, if you don't have your iClicker today, or if you run out of batteries or forget it one day, just write the questions down with the answers on a piece of paper and put your net ID on the paper and your name, and then hand it to me after class. So don't worry if you don't have yours today. So also don't be nervous about if you get the answer right or wrong. A lot of them are just, I just want you to think about, anticipate an answer and just relax and just don't just randomly click, but just try to get it right. But it doesn't matter if you do or not. You get full credit if you just answer all the questions. All right, so that's the idea, and you register it on Compass. And why don't we just make sure that this is working on this first day that we're trying it. So I'll look at this. Here's a question, and I'll start this. So it says you're supposed to be on double A. And if you're not, excuse me, press and hold your power button down for 2 seconds, and then press A and then A again. So if anybody doesn't have that base frequency, here's the instructions for getting it on that base. I think most everybody automatically has that. So, all right. And now, so this tells how many people are answering the question, yeah. So I'm curious how many people have taken Stat 100 here and whether you did it online or in person. Just answer A, B, or C. If you're having problems with your iClicker, ask your neighbor. They'll probably know more than me since I've never been in your shoes. I think when it registers, if I'm not mistaken, doesn't it turn green or to know that it registered? Is that true? Like if you click it. All right, so far we've got 90 people. Has everybody done it? Okay, so that must be everybody here. And so now, I guess what I do is I can stop it and then click on the results here. And how come it didn't show me the results? Oh, there it is. Okay, So most people said no, but 23% actually took it in person and 4% took it online. So about a quarter of the students in this class have already seen the first third of what we're doing. So you guys should be pros at it, a quarter of the students. All right, now let's go back to the document camera here, or go to the document camera, and here's where we left off last time. We left off at the end of observational studies, and we saw, we saw, we're comparing observational studies to experiments. And so just to summarize here, and to help you with the homework that's due tomorrow night, let's look at some differences. So observational studies, this is on page 14, versus randomized experiments. And, okay, so the main difference here is what? That the treatment and control group in randomized experiments do not have systematic differences. And in observational studies, they do, because the people themselves choose. So there's bound to be differences between the two groups that could affect our results. So the treatment and control groups, they start off different in systematic ways, different from each other. Remember, we want them as alike as possible. And here in randomized experiments, they're better because the treatment and control are more alike. Treatment and control are alike, and they do not have systematic differences. The differences that they have are due to random differences, and they average out in the long run. But they could go in either direction. They're not systematic. They're not biased. They're just chance errors, chance differences. So it's without systematic differences, without bias. So that's a big difference. So if they start off alike, you want to keep them alike. They don't, first of all, they don't have confounders. They have no confounders because they don't have those systematic differences. And the observational studies are likely to have confounders. They're very likely to have confounders. Those are the differences, those systematic differences between the treatment and control group. So you don't know at the end whether those differences are causing your response or whether it's the treatment that's causing your response. So these confounders are differences that are both related to the, are both differences between the treatment and control group and differences in the responses. Okay, so there's no confounders, there's confounders here. So what do? How do we, stratification helps us remove that confounding in observational studies by comparing subgroups for which the confounder is the same. So here, subgroups, if you break into subgroups here for observational studies, they help make the treatment and control alike. They eliminate that confounder. So you want to compare treatment versus control within the subgroups, right? And you don't want to trust the overall result because that's confounded. So you want to, you look at subgroups, like within the subgroups, you compare the treatment and control group on the response to see if the difference still holds up or disappears. So you don't trust the overall result, right? The overall result, don't trust overall result. The overall result may be so confounded that it gives you the opposite result from the truth. And that's that paradoxical situation we saw with Simpson's paradox, where it looked like smoking actually helped you live longer. But once you controlled for the confounder of age, it was the opposite. So it reversed the effect. So there's an example in your homework like that. Whereas with randomized experiments, since they start off alike to begin with, they don't have confounders. You don't want to break into subgroups because you'll introduce bias. This happens all the time with people in a randomized experiment. If they drop out of the experiment, who do you, very often, what do you do with people who drop out of a randomized experiment? They're called non-adherers. They don't stick to the program. And you want to include everyone. The overall result here is the valid result. Why? Because it starts off this randomized experiment, but if you break it into groups between who adhered and who didn't, then you're looking at self-selective groups and you're introducing bias. All right? That's called intent to treat analysis, and it's really important. It's not intuitive because you think, how can some treatment work if the people don't stick to it? So you want to compare, you'd think you'd want to compare people who stuck to it in the treatment to people who stuck to it in the control group. You'd think that's what, and sometimes that is okay, you'll get the same results, but often the treatment itself is different than the control, than the placebo, and so there's different motivations to stick to it in one group versus the other, and then you introduce bias. For example, if the drug had side effects, pretty bad, worse side effects, well then people are going to be more likely to drop out of that group than they would the placebo group. So you have to compare overall to overall. That doesn't mean you don't look at the subgroups, but the subgroups do introduce bias. So you have to be careful about that. They introduce bias. Why? Because they break the randomization and introduce self-selection bias. They introduce. That word's introduce bias because they break this ideal randomization. So the idea is that in this case, you do trust the overall results. So it might seem like we're telling you contradictory things, trust the overall results in one case, in the other case don't, but it just depends on what you start off with. If you start off with this great experiment, you don't want to ruin it by breaking into subgroups. But if you start off with observational data that's already mixed up and confounded, then breaking into subgroups, stratifying helps you. I know there's lots of terminology, but I'm just trying to get at the logic here. So that's the idea. Anybody have any questions about that before we start the new chapter? Okay. So now we're going to start stuff that many of you are already familiar with, whether you've been in Stat 100 or not. And that's descriptive statistics. It's just summaries. You have a bunch of data, and you just summarize it either numerically or graphically. So let's look at numerical summaries first that are measures of the center of the distribution of the list of numbers, okay? So we're going to look at the mean and the median first. But before we do that, I just want to talk about the notation we're using. So there's parameters and there's statistics. And parameters are these numerical facts, parameters about the population. You can remember because P and P, population, about the whole population. Then statistics are numerical facts about the sample. All right? Now, right now, we're just looking at descriptive statistics. So this distinction is not important at all. It's not important. We can just assume we have, like we're just going to look at a list of numbers. We didn't take a sample from a larger population. So you can just, this is the whole population. These are all the numbers we're interested in. So this distinction really doesn't come up. You can just think of it, we have the whole population. It comes up when later on, next week or the week after, when we start doing inferential statistics, when we're trying to infer population parameters from sample statistics. And then there's a slight difference there. And what people generally do is if you have all the data for the population, they use these Greek letters, like for the average or the mean, they use the letter mu. And for standard deviation, sigma, Greek, sort of the ideal population out there. And then for a sample, they generally use Roman letters, so they'll use X bar actually for the average, and S for the standard deviation. But that's right now, let's just assume we have this is the whole population, so we don't have to worry about it, okay? So you know how to find an average. Find an average of this list of numbers. Here it is in symbols, and then find the median. Okay, let's just do an iClicker on this because I think you know it already. So let's just go to here. Now, why isn't this working? I knew this was going to happen to me. See? It's already gone to the median. All right, here we go. So what's the average of this list? This list of numbers is the same ones you have in your notebook. So I'm just doing the problem on page 15. Now there's more people answering the question. You should answer every question. Okay, it looks like people have stopped. Just pick an answer if you haven't already. Okay, and we'll stop it. And see what you chose. Okay, so everybody got that right. They just added the numbers up. And you get -7, and then they divided by 7. So just about everybody got that right. Good. Let's go to the next one. And the next one. Why isn't it doing it? Okay, so what's the median of this list of numbers? So let's start that off. Okay, so we can stop this now. What if I just do this first? What happens then? Oh, then you can still change your number. Change it. Okay, let's stop. We want to stop it. All right. So here, oh, I see what people did. Okay, so people think it's the middle number. That's true, but it's the middle number once you list them in order from smallest to largest. So let's write that down in our notebook. So the answer is 0. This is correct. This is the answer. So let's look. Let's go to the notebook. And all right, so everybody got this average correct. You just add up all the numbers and divide by however many there are, and they got -1. But here, it's important. People knew it's the middle number, but it's the middle number when you arrange them from smallest to largest. So you first have to list them in order, and then it's the middle number. Easy mistake to make. Okay, so now, so what if you have no middle number? If there's an even, this has an odd number. Here there's an even number, so there's two middle numbers. This one and this one are both the middle numbers. So what do? So you take the average of the two middle numbers. So in this case, the median is going to be equal to 6 plus 10 divided by 2. Halfway between those two, and that's 8. So that's what the middle number is. So now, what's the mode? The mode isn't used very often. We're not going to talk about it very much at all. It's just the most repeated number, the most common number. There can be multiple modes. If there's here, the most common number is 0. So if each number is only repeated once, then I guess they're all modes. It's not used very much, but I just figured I'd put it up there. Okay, so any questions so far? So now, let's look at some properties of the mean and the median. So these are properties of the average and the median, the mean and the median. All right, so it says if a constant is added or subtracted to each number on a list, what do you do to find the new mean and median? Well, you just add or subtract that same constant. So let's just try it with a simple example, because I think the concept, you'll see it right away. So let's say you have a list, super easy list of 1, 2, and 3. And then let's say you add 10 to each number on the list, to each of the 3 numbers. Then you'll get the numbers 11, 12, and 13. Okay, so here, what's the median? The median's 2. It's the middle number. And what's the mean here? Well, the mean, you just add them all up and divide by 3, and the mean is 2. When it's symmetrical like this, they're the same. Now, when you add 10 to each number, what happens? Well, the median is just the middle number here, so the median is just the old median plus 10. That's the rule. So that's 12, and the mean is also the old mean plus 10. And that makes total sense, because if you add, the same number, add or subtract the same number to the list, and then the mean and the median would just go up or down by that number. That makes complete sense. Now, how about if you multiply or divide by a constant? What would be the rule then? Well, let's think about it. Let's do the same list of numbers, 1, 2, 3, and let's think about what happens if we multiply each number by 10. So we multiply each number by 10. What would that do? You'd get 10, 20, and 30. So what would happen? Well, you can see right away that the median just gets multiplied. It's the old median multiplied by 10. And same with the mean. It's the old mean multiplied by 10. So those are pretty obvious and pretty straightforward. But here's a difference between the mean and the median that's important to understand, and that is that the mean is sensitive to extreme values and the median is not. So let's see what happens to the same list, 1, 2, and 3. If we add, let's make it even more extreme. Let's say we add 300 to the largest number on the list. So let's just do that. So now we're going to do what? We're going to add 300 to the largest number and keep the others the same. So we still have those 3 numbers, but now they're going to be 1, 2, and instead of 3, it's going to be 303. So we added 300. do you see how the median is still doesn't change? The median is still equal to 2. It's the same. It's the middle number. But look at the average. Look what happens to the mean. The mean is going to go up a lot. It's going to be the old mean plus, what have you done? You've added 300 more to the sum, right? The old mean, but you've put 300 more in, so it's going to be 300 divided by 3. So it's going to be 102. This is 306 divided by 3 is 102, and this is just 6 divided by 2, divided by 3. Okay? So the median does not change. That does not change. So it's really, I mean, this is an important point because to distinguish whether you're interested in the median or the average. And people can get very confused. Often with income, this comes up because there's often extreme values. So when you're talking about income, the average and the median are very different numbers, and you have to be think about what you're interested in. Yeah? Yeah. So these rules, yes, these are the properties, and they're summarized. Her question was, what are the rules here? And let's see. Yes, right here on page 18, they're summarized. It says when the same value is added or subtracted to all numbers on a list, the average increases or decreases by that value. And it also says here, extreme values have a strong effect on the average. The average moves towards the extreme values. Okay? But the median stays as the middle number. Here, let's think about it this way. What if I added 3 million? Would the median change? No. Right, so the average is affected by every single number on the list. So if you have very skewed data with these extreme values, you might want to focus on the median more than the average. Okay? So let's move on now. How about the standard deviation? Well, now this is a numerical summary of the spread of a distribution. This is how spread out it is, the standard deviation. But there's also something called the variance and the range. The range is the simplest measure of the spread, and all it is the largest number minus the smallest number. It just pays attention to two numbers. It's the simplest one. So find the range of this number. The range would just be, all you do is focus on the biggest number minus the smallest number. It's always positive, so the biggest number is 2 minus the smallest number, and the range is 7. It doesn't matter what the other numbers are. So clearly that's not a very informative statistic because it only pays attention to the minimum and the maximum. So the standard deviation is much more widely used, and that pays attention to every single number on the list, and what it does is it measures the distance. It's a measure of the distance each number is from the average of the list. It's a good measure of that distance. So it's not quite the distance, but it's like the distance. Okay, so I'll say it's like and I'll explain why it's not exactly the distance in a minute. It's like the average distance. All the numbers are from the average, or from the mean, I'll say. All the numbers that are from the mean. And you'll understand this when we calculate it in just a minute. And the variance is just the square of the standard deviation. So that's all that is. It's just the standard deviation squared. Okay. So let's do an example, and you'll understand what I'm talking about here. So now we're on page 17. And before we do an example, just to get a picture here, let's look at example 6 here. It says, which of these distributions, these are, we haven't really talked about that, but these are just histograms or sketches of histograms. Which one do you think has the larger standard deviation? So they both have these averages of 0. And do you see how the numbers here are all bunched up around 0 more, and here they're more spread out around their average? So distribution 2 is going to have a bigger standard deviation because the numbers are more spread out. These are all bunched up around 0. All right, here, you'll understand this better once we compute a standard deviation. So, so here's how to compute the variance and the standard deviation, and here it's in words, and here it's in symbols. Assuming that we have all the numbers on the list, we're not trying to estimate an unknown standard deviation of a population, we just have the population. So I wrote it in the Greek letters here. So let's start off with this example, and you'll see how it goes. All right, so you have this list of numbers. You have a list of 7 numbers here. And the first thing you want to do, if you want to find out how spread out they are around the average, find the average. So let's just find the average. You can call it mu, but we'll just be simple here. So the average is equal to, you're just going to add those all up, and you get 21, and then you divide by 7, and we find out the average is 3. And you could have just eyeballed it and see, because it's right in the middle, and it's symmetrical around 3. All right, so now the next thing you want to do is to get these distances or deviations from the average. So we'll get the deviations. That's our next step. And how do you get the deviations? Well, it's just the distance from the average. For example, the deviation for this number, there's going to be 7 deviations. How far does 0 deviate from the average, from 3? Well, it's a distance of 3, but the deviation takes into account whether it's above or below. So this is below, so it's going to be negative. So it's actually, the deviation is the number. These deviations are the number, the value minus the average. So if it's below, it's going to be, the number is 0 minus 3, so that's negative 3. Negative, then you have 1. This is 2 below, negative 2, negative 1. 3 is right at its average, so it has 0 deviation from the average. And now 4 is 1 above. 4 minus 3, 1, 2, and 3. So those are the deviations. All right, so these are the distances, and what you want to think about is, okay, what's the average distance here? I said it's like the average. But if you include these signs here, look, the deviations are going to sum to 0, so the average distance is 0. And that's always going to be true, even if they're not symmetrical like this. The negatives and the positives will average out, and you'll get 0. So clearly, you can't just take the average there. That's an important point, so we should remember that. It's a good way to check that you computed them right. Check to make sure they average to 0. Okay, so they always sum to 0. So clearly that's not a good measure of, you want to get rid of the signs. So you'd probably think the easiest thing to do is to just neglect the signs. Take the absolute value and then take the average. And if we did that, we'd add them up and get 12/7. Well, the only reason we don't do that, actually you do that in certain circumstances when you're interested in certain, for certain statistical methods, particularly if they involve the median instead of the average, you do something like that. But for by far most things, you don't do that. Instead, to get rid of these signs, what people do is they square each deviation. And the reason, so they square them all, and that gets rid of the sign. But of course, that's going to give you the squared deviations. So, and the reason people do that is just because it's mathematically, the squaring function is easier to work with than the absolute value function, especially if you think about the way it's shaped. When you square, it has differentiable everywhere, whereas the absolute value function doesn't have a derivative at 0 here, so it just comes to a point. So it's just the absolute value function is very hard to work with mathematically, and that's the reason that people don't do it. All right, so we square instead. So let's take these deviations. Long story short, we square. And we square them. So now when you square each deviation, they come out positive, of course. And now we take the average of these instead of the absolute values. We take the average of these, okay? And that's called the variance. It's called the variance. So you just add all those up together. Now you get 28 over 7, which is 4. So that's your variance. But now you're in squared units. And it's, like let's say these were, I don't know, the number of your answers to the question, how many pets you had or something. If you said, okay, our average is, people average 3 pets, give or take 4 squared pets, it doesn't make sense. So it's not very intuitive, this variance, even though it's extremely nice mathematically, and we're going to be working with it all the time, the variance, when we're doing calculations. We're going to be working with these square deviations. But intuitively, we want to, give a measure back in the same units, not squared units, so now you take the square root, and then you're back here. So the square root, so the standard deviation is just the square root of the variance, and that's 2. So that makes sense. Look at these, look here. On the average, these numbers deviate about, looks like about 2, right? You have some deviations that are as much as 3, some that are 0, but on the average it's 2. It's actually not 2, so we should note that if you actually, how this compares to really taking the average of these deviations, at the average of the absolute value. So note, the SD, if you do this, is always a little bit bigger, is just a little bigger than the average of the absolute value of the deviations. Okay, so it's a nice way, to know that you're in the same ballpark. You can do that. You can say, okay, if you took these absolute value of these deviations, you'd get what? That would be equal to what? 3 plus 2 plus 1 plus 0 plus 1 plus 2 plus 3. And as we said before, that adds up to 12. Divide by 7, and you get about 12/5 or 1.7. 1.4 actually. So that's how it compares. It's always just a little bit bigger. So that's the idea. Any questions on that? So now a lot of you are probably wondering, we're taught that you divide by n minus 1 here, like 6 instead of 7, and that will come up later when we're talking about estimating a standard deviation of a larger population in Chapter 13. Yes? Good question. So she asked, how are we going to have to calculate this on our own very often? You will, at least on the homework you have to do it, and on the exam you will have to do it. So I think it helps you understand what it is if you do know the procedure. Yes. So yes, you will have to learn how to calculate it on your own. You can check with your calculator if it has that function. I guess it would on the calculators that you bring to your exam. But I could ask you, like, list the deviations or give you steps. Yes, another question. Go ahead. Could you repeat that question, please? I'm sorry, I didn't hear it.
It's fine. So what do these numbers really mean? So you have like deviation, you have words like deviation and standard deviation and variance. But what do those numbers really stand for?
What do the numbers, was your question, what do the numbers really stand for, the standard deviation and the variance?
Yeah, what's the point, I guess?
What's the point? Oh, what's the point? Well, wouldn't you be interested in, like if I told you the exam scores in this class were, he says, what's the point of this? Let's say I told you the exam scores in this class had an average of, oh, I don't know, 80. Wouldn't you be interested what the spread is? The average is 80, but wouldn't it make a big difference if I said give or take about 1? It's like a margin of error. That would mean most people were between 79 and 81. Or if I said give or take about 10, had a standard deviation of 10, then you'd think most people are between 70 and 90. So it's going to be very useful because you don't just want a point estimate, you want to attach not only a point estimate, but you want to attach a margin of error to that. And we're going to be able to see how not only are we going to be able to attach a margin of error, but we'll be able to say basically what percent of the population is within that margin of error. Does that help you? Yes?
I was just saying, I think what he meant was, he was trying to ask, like, what the standard deviation is, like, what percent. I think that's what he meant.
I don't know. Did I answer your question? Yes or no? The last one? I think, thank you for trying to clarify his question, but I think we did a good job, okay? All right, let's move on. Okay, so now we're going to look at these properties of the standard deviation. And so if you add or subtract the same constant to every number on the list, what happens? The standard deviation and variance don't change. The average changed, but the standard deviation didn't. Let's try it with this list. We calculated. We know the standard deviation is 2. Let's see what happens if we add 10 to each number. Okay, so let's just check it out and see why this is true. Okay, so now we're going to do the same thing. We'll add 10 to each number. So what happens if I add 10 to each number? Then I'll just get 10 through 16. Now, did the spread change? The average certainly changed. It went from 3 to 13. But if you subtract off the average from the list, you're going to get the same deviations. 12, you're going to get, -3, -2, -1. The deviations are the same. The spread is the same. So even though the average changed, the deviations don't. Because remember, the deviations are the distance from the average. So the spread is the same. The numbers just shifted up. So the standard deviation and the variance, which are just measures of the spread, are the same too. Okay? Does that make sense to everybody? Does that convince everybody? The spread doesn't change. It just the numbers just shift up. Their spread is the same. But what if you multiply or divide? So if you add or subtract, they don't change. But what if you multiply or divide? Then it says it would be multiplied or divided by the absolute value of that constant. So let's try that. So let's take our numbers again. 0, 1, 2, 3, 4, 5, and 6. And now let's multiply each number by 2. Okay, if we do that, 0 times 2 is 0. 1 times 2 is going to be, I'm going to make it look like it's on a number line. So it's going to be 2, and then 4, 6, 8, 10, 12. So now instead of the numbers going from 0 to 6, they go from 0 to 12. And the new average is multiplied by 2, and also the deviations. Look, this is now 2 away, now 4 away, now 6 away. They get multiplied by 2. So it gets multiplied, the spread doubles, and if you tripled it, the spread would triple. The spread doubles, so the standard deviation does. Now, what if it was by a negative 2? By a negative 2, what would we get? If you on a number line, it would be 0, then you'd get negative 2, negative 4, and all the way down to negative 12, right? But remember, the standard deviation is always positive, right? What would a negative standard deviation even look like? If it's measuring the distance, the spread around the average, what does a negative spread look like? And besides, you can see by the calculations of squaring it that the standard deviation is never negative, never. Okay? Does that make sense to you? That it's never negative. Okay. So that's right here. So now if you multiply or divide every number on the list by the same constant, okay, so here the standard deviation doubles here, but what would happen to the variance? So the variance is the standard deviation squared, so it would be multiplied by 4. So if you multiply, in this case, if you multiply or divide every number on the list by the same constant, right, let's say it was 6, then the variance would be multiplied or divided by that same constant squared, by 36. Now this last point is another reason, there's another advantage to using variance instead of standard deviation, and that's why we're going to be using sum of square differences, a huge amount in this course, and we're going to be using, because it has a nice mathematical property in that the variance of the sum is the sum of the variance, and that's not true. The variance of the sum is the sum of the two variances, and that's not true with standard deviations because it's not true. If A and B are independent, this is true. But if A and B are independent, the square root of A plus B is not equal to the square root of A plus the square root of B. So the variance is much, much easier to work with. And the proof of this, it's a really simple proof. And so I just wrote it in a very easy way. And if you want to look at the mathematical proof of it, it's on See Proof on page 228. So you can look at that, but you're not responsible for knowing that proof. Although I'm sure if you get into, in higher level classes, you will be. In 400 level. All right, so let's look over our summary here. And let's see what we have. So we saw the mean in skewed distributions, the mean and the median are going to mean something very different. And we're going to look at, with extreme values, when the extreme values are very big. We haven't looked at the histogram has a long right-hand tail and the average is larger than the median. We're going to look at this on the next page. Okay? Now, the standard deviation measures the typical spread of the deviations from the average. It's usually just a little bit bigger than the average of the deviations, neglecting sign. We saw that. 2 is a little bit bigger than that 1.7. And the standard deviation is calculated, you'll see this term, by taking the root mean square of the deviations. The root mean square. What do I mean by that? We'll be seeing that term come up a lot, so we might as well look at it here and see it refers to, you're taking the root right here, the R is for the root of the mean, the average is the mean, of the mean, that's where the M comes from, of the square, yes, of the deviations. It's the D. So you're taking the root mean, you're taking the square root of the average of the squared deviations. All right, that's the root mean square of the deviations. Let's see what else we want to do. It's never negative, and it has the same units. Okay, let's do an iClicker. It's never negative, but can it be 0? Let's do an iClicker about that. So get out your iClickers. And got to get rid of this, sorry. Okay, we'll start this. Okay, so I think I'll stop it now. So just choose a number if you haven't already. And let's see what people answered. Very good. Yeah. When they're all the same, then the average is that number, and they all deviate 0 from the average. It's certainly true when the numbers are 0, but it's not only true then. Okay? So if every number is the same, if you all got 80s on the exam, I said the average is 80. Let's say every single person got an 80 on the exam. Then I would say the standard deviation is 0. And then you'd know, hey, if I take that exam, you know, I'm probably likely to get an 80 like everybody else. Right? Okay, so that's, let's move on. Let's go back to the notes. And just finish up the summary here, back on page 18. And let's see, this is very important because when I ask you to, when you compute the deviations, make sure they sum to 0. And this is going to come up over and over and over again, that we're going to be looking at deviations from means, and the sum of the deviations is always 0. All right, and of course these are important. This is all important. Why don't I just say, for all the summaries, read it. They're always, every point is important. Okay, let's move on. Now we're going to look at, okay, so we finished up numerical summaries of the data, and now we are going to look at graphical summaries of the data, all right? And in this class, we're just going to concentrate on histograms. We're not going to look much at bar graphs or box plots. We're just going to mostly focus on histograms for in Stat 200. All right, so histograms are used to graphically display quantitative data, all right? And they use areas to depict the percentage of data with any particular class interval. Now, the difference between a histogram like this and a bar graph is that this x-axis has meaning. These numbers are drawn to scale. These are is a histogram. It shows the distribution of a class, their scores on a final. Okay, so it says right here that this block of people scored between 0 and 50, and so this is 5 times longer, the width, than the block of people that shows how many scored between 50 and 60. On a bar graph, the x-axis just represents categories. They're all the same, all right? And that's useful for categorical or qualitative data, like how many people in the class whose favorite color is blue or green or something. So we will be looking at bar graphs in that context. But when we have quantitative data, we're going to be using histograms. All right, so that's the x-axis. What's this y-axis? Well, this is the density, or how crowded each interval is. Okay, so this represents, in this case, this is points, and this is percent per point. So for example, let's look at this. Okay, so this goes up to 0.5. I'll put it here so you can see it better. So this, in this interval, within this interval, it says that 0.5% of the people scored with any particular unit in here. Like 0.5% of the people scored 25, 26, any number in here. That's what that number stands for. And here, this is 1, this is 1, this is 2.5. I'm just, because it's hard to read it going across. This is 2, and this is 1 again. So this is the most crowded interval. Like the area right here looks about the same as this area. If we wanted to figure it out exactly, how would we figure out the area of a rectangle? Right? The area of a rectangle is the width, you all know, times the height. So in this case, the area would be 10, the width is 10, 80 to 70 is 10, times 2.5, so we'd get 25% here. And here, you'd get 50 times 0.5, and you'd get 25%. So you can see that these two blocks have the same area. A quarter of the people scored between 70 and 80, and a quarter of the people also scored between 0 and 50. But see how much crowded this interval is? Think about the people all being stacked on top of each other. It's very crowded, whereas here they're more spread out. So this is the density right here. That's what this measures. And this is a histogram with discrete data, but if you have continuous histograms, we'll talk about continuous versus discrete data in a minute, but if you have continuous histograms, they're known as, continuous histograms are known as probability density functions. Okay? And we'll see that later. We're mostly, we're not, but right now we're looking at this discrete data where people actually got a score. There was a whole number or a whole number and a half or something. All right, so let's see. Often you won't even see this vertical axis because an important point of all histograms is this, that the total area of all the blocks adds up to 100. So if you know the area and you know the points, you can figure out this density. You could express it differently. You could change these points, express these as half points. So I'd have, instead of 0 to 50, I'd have 0 to 100 half points. And then I'd say percent per half point. And you could just change the scale if you want. So often you don't see that. But I'm going to give it to you because it's much easier to figure out percentages with this there. Let's see. All right. So what percent of the students scored between 80 and 90? Well, what do you think? I just should have done this as a clicker. What percent? Well, it's going to be what? Its area will be 10. And look, it's 10 points. Between 80 and 90 is 10 points times 2% per point. So you can see how these cancel out and you end up with 20%. All right, so let's fill that in. So this is 20%. And now each of these is the same area. Each of these is the same, and what is it? 10 times 1. So 10%. Now let's make sure that they actually do add up to 100. Otherwise, we've made a mistake. So on an exam, for sure do that. Just always make sure. And let's see, 25, 35, 45. And here we have 65. 55, excuse me, 45 and 55, so that's 100. Okay, what percent scored exactly 83? So you have to assume an even distribution in the interval, which probably isn't true, but just assume it is. I mean, I doubt it's true here, that there are just as many people who scored 0 as 50, but let's just, for the purposes that, let's just assume an even distribution. And if we do, then what do you think it is? Well, this tells you percent per point. 83 is right in here. And that tells you 2% for each of the 10 points in here. That's how you get 10 times 2 is 20%. So for 83, it's 2%. It's the same as the height of the interval. Okay? You could say 83 is 1 point. So the width is 1 times the height 2, and you get 2. Yes, question over there. I just, for working these problems, I just want you to understand what this density is doing. If I blocked it this way, just assume. If you actually looked at the histogram and broke it up into other blocks, it's not going to look, I'm just saying the data is not given to you here. So if the data looks like this is what you have to assume. You can't speculate. No, you can't. With this kind of graph, you'd have to know like the height for each one of these. So, but we're not going to, yeah. And you would be doing that in higher level courses. You would, multiply each value here times its height here. But for this, I'm just showing you, giving you an intro, good feel for it. Okay, so assume, yes, her question was, should we assume that it's an even well, you can't really assume that unless I tell you. I say it. How's that? And I told you it here. Yes, there's another question back there. Yes, go ahead. Oh, where do you put 80 or 80, which?
I just don't know where I should put the 92.
Yeah, okay, so her question is how, how should she divide this up? Is 80 in this interval or is 80 in that interval? Is that your question? Like these dividing lines. And usually I should tell you, I didn't hear, I should tell you that the intervals include either the left hand or the right hand. We'll look at I didn't hear because it wasn't relevant to this example, but I should have said, okay, intervals include probably, maybe if nobody got 100, I'd say they include the left endpoint, but not the right. So for example, this interval 90 would be here, not there. That would, if somebody got a 0, it would be included in this interval. Okay? Here, we're going to do it here. The next page has it, so why don't we look there? Okay, I didn't include it in that example. Good. Her question was, I didn't give a rule for the dividing lines, but you usually do. You say whether the class intervals include left endpoints but not right, whether they include right but not left. And I'm doing it here on the next page. Does that answer everybody's questions? All right, let's go to it then. Now we just learned how to read a histogram, and now let's draw one. Okay, so the table below gives the GPAs for high school students, class of 500 students. So there's 500 students here, and this is how they break down in terms of their GPA. Fill in the table below and then draw a histogram representing the data. And you're going to have to do this for your homework. The class intervals include the left endpoint but not the right. For example, this interval includes students with GPAs of 2 but not those with 2.5. All right. Now, so how are we going to do this? Well, first of all, here's our graph, and here's the intervals we have. So we start off at 0, from 0 to 2. So let's just say it's 1, 2, 3, and 4. So this is 0.5, 1.5, 2.5, and 3.5. And the first interval goes from 0 to 2. So it goes all the way up to here. And I have to figure out how high to draw this block. And the next one goes from 2 to 2.5. It's going to be a skinnier one. Then this one's going to be, okay, it's going to look like that. So now, first, what percent of students, the area represents the percentage of the students in each block. So what percent of are in the first block? Well, 50 out of the 500 are in the first block. They did pretty terrible. So that is 10%. And then 150 out of the 500 are in the next block, and then 50% are in the next block, and 10%. And of course, it should add up to 100%, and it does. Now, we know the widths of the interval, 0 to 2 points, that's a width of 2 points. 2 to 2.5, that's 0.5 points. This is 1 point wide, and this is 0.5 points wide. Okay, so we've got that. Now, the height. Well, we know that the area is equal to width times height. So height is equal to area divided by width. So we can just divide our area, 10%, by the 2 points. And you can see again, that's where we get the height as a density. 10% divided by the 2 points, and that gives us 5% per point. Okay? So we know this density axis is going to be in percent per point. That's what this is going to be. And so the first one of them is 5. The next one would be what? 30 divided by 0.5, so that's 60% per point. The next one is 50 divided by 1, that's 50% per point. And the last one's 10 divided by 0.5, so that's 20% per point. Okay, so we can label them. Let's do that. So this is going to be 10, 20, 30, 40, 50, all the way up to the top one is 60. All right, so now we can draw the histogram. Between 0 and 2 is 5%. So that is only 5%. Oops, excuse me, it's 10%. It's 10%. It's a height of 5% per point. It's 10% of the area. So we say, right, 2 times 5 is 10. So that's 10% of the data. Now the next one goes up to 60, and it encompasses 30% of the data. It goes to 60, and it's 30%, right? A half times 60 is 30. And the next one goes all the way up to 50. A width of 1 times the 50 is the height gives us 50%. And the last one goes up to 20. Right? And it's a half times 20 is 10%. See, those match. And they add up to 100. So that's the idea. Any questions on that? So you're going to be drawing the histogram on the computer. Now, is this the interval that has the most people? Is this one, but it's not the tallest, right? It's not the tallest but it has the greatest area. Now, getting back to how the average and the standard deviation changes, what if we added 1 point to everyone's GPA so that GPA could go up to 5, assume? How would the histogram change? Would the average change? If you add 1 point, of course the average is going to change. Yes. The average would what? It would go up by 1 point. But do you think the standard deviation would change? What do you think? No. And can you see why? This would just be shifted. Every single point, everything would be shifted, so it would go up to 5. The whole thing would be shifted, but the shape would stay exactly the same. So no, the histogram shifts, but the shape is the same. It shifts 1 point to the right, but the spread is the same. The spread is the same. Can you read that? The histogram shifts, but the spread doesn't change. Now we're going to do this next one as an iClicker, so you can get ready. If you want to look at the picture here, thinking about the next one is, if you add 1 point to only those in this block, in the what? 0, you're adding 1 point to these. So this block would shift what? All the zeros? Oh, adding 1 point to this, right? So 0 would go to 1, would go there, and it would get shifted over. This block would get shifted over. So think about what would happen. All right, let's go to the okay, if you added 1 point to only those in the 0 to 2 interval, how would the average change? You don't have to compute the average, just how would it change? Would it increase, decrease, or do you think it would stay the same? Whoops. Okay, I think we can end it now. And let's see what people chose. Yes, the average would increase. If you even increase one number, think what the average would increase, right? Even if you increased one number on a list, the average would increase because the sum goes up and you're dividing by the same number. So the average would increase. All right, let's look at the next one. How about what would happen to the standard deviation? If you added 1 point only to those, think about how the spread would change. Shoot, we only have 5 minutes left. Darn. Okay, I'm going to end this now, so just vote. And what would happen? Let's see, the standard deviation would decrease. Why would the standard, most people got it, let's look. Just think of the picture, and we'll go to the document camera. Think of the picture. Look, you're not affecting these people, right? You're just taking these people and moving them up. So do you see how the spread, there'd be nobody down here. The spread would decrease. So that's the answer. The standard deviation would decrease and the average would increase here. All right, now, let's move to the next page. And let's think about, on a histogram, let's just finish this page here, and this will be the end of this chapter. And we'll do one more clicker. All right, so the median divides the histogram into two equal pieces because it's the middle number. So there's 50% on each side. And the average is where the histogram balance is. Now, they'll be the same if the histogram is symmetrical. The median and the average are the same, okay? But if it has a long right-hand tail, if it has these extreme values, like if there was in this class, if Bill Gates walked in and they asked you like your income, walked in, so he would be an extreme value out here. Most of us would be somewhere here. That's going to make the average the middle person would stay the same, but the average is going to go up. Whereas like on our exam scores, most people do pretty well. But then there's some people who don't show up or they just do terrible, like in the teens, just because they're not paying any attention. And so then the extreme values this has a long left-hand tail. And then the average is less than the median. They lower the average there. Okay, so now let's just do one more clicker question here. And we'll go, let's look at that. And okay, so the histogram shows your survey responses to how much cash you have in your pocket right now. Whoops. How much cash? This is like this is from your survey data. So in this, it looks like a lot of people didn't have much cash, but there's some people who had $1,000 in their pocket. I don't know what they're doing with that money, but anyways, so answer, do you think in this histogram, how do you think the average compares to the median? Do you think it's greater than the median, less than, or the same? What do you think these extreme values do to the average? Okay, answer quickly so we can look at the results before. Okay, so, all right, let's look at the next question. I just want to show you. Okay, we stop it here. All right, I bet most people said, sorry. Anyway, what happened? Anyway, the average is greater than the median. I hope it recorded those last responses, but if it didn't, you'll all get credit. And here, let me show you the results. So here was the results. The median was only 30, and the average was 114 of the responses. All right, so see you next time.